Okay, we're on to chapter 14, and we're going to talk about the logic and theory that go behind statistical significance tests. So, a statistical significance test, also known simply as a significance test or as a hypothesis test, is an inferential statistical procedure conducted to determine how likely it is that a study sample result is due to chance, which is to say, to luck. Prior to going into significance tests in more depth, we need to do a quick overview of probability. So one can calculate the probability of an event by dividing the number of events with a given characteristic by the total number of events. Here are a couple of formulas for probability. The symbol for probability is a small p, and it's the same as the symbol for proportion, as the symbol for proportion is presented in this text. Probability is really one and the same as the proportion of events with a given characteristic. Let's calculate probability in the simplest of situations. 10 therapists attend a staffing on a given case. 4 favor intervention by group therapy, 6 favor intervention by individual therapy. A supervisor puts names in a hat. She shakes the hat and draws out the name of a therapist. What is the probability of picking a therapist who favors group intervention? We have 4 therapists who favor group, which is to say 4 events are group. We have a total of 10 therapists. So we can think of this as the total number of events. So the probability of picking a therapist who favors group is 4 divided by 10, or 0.40. What is the probability? That an unbiased coin will turn up heads. So here P would equal 1 side, the event with the characteristic of interest, heads, divided by the total number of sides, 2, and P would calculate to 0.50. Probability can range from 0 to 1. So when probability is 0, there is no chance of the given event, where probability is 1. There is certainty, that is to say, a 100% chance that the event will occur. Let's connect probability and the normal distribution. What is the probability of randomly selecting a case from a normal distribution that is located within 1 standard deviation of the mean? So, as you know and remember, 68% of cases are located within 1 standard deviation of the mean. We can divide that percentage by 100 to determine the proportion. So the proportion of such cases is 0.68. Probability and proportion are one and the same. So the probability of selecting at random a case located within 1 standard deviation equals 0.68, or expressed with our symbol for probability, P equals 0.68. And here's a visual presentation of our calculation and work. Given a normal distribution, what is the probability of selecting at random a case whose value is located 1.50 or more standard deviations below the mean? And in other words, what's the probability of selecting a case with a z-score of minus 1.50 or lower? So we can solve this problem consulting the normal distribution, table. So consulting that table, we find that the percentage of cases with z-scores of minus 1.50 or lower is 6.7. The proportion of such cases, therefore, is 0.067. Proportion and probability are one and the same, thus p equals 0.067. Our probability is 0.067. Now we're moving back to significance testing, also known as hypothesis testing. So each hypothesis test, or we could say significance test, has a null hypothesis and an alternative hypothesis. These two go together to form a hypothesis pair. Now, null states that some given condition is true in the population. The alternative hypothesis, in essence, negates the null. It states that the null is false, or viewed differently, it states a logically opposite condition. So here's an example of a hypothesis pair. Note that both hypothesis statements in the pair pertain to the population from which the sample is selected. So, in the population from which the study sample was selected, the mean score on the XYZ scale equals 100 points. So that's a sample null hypothesis. So the alternative hypothesis has got to state the logically contradictory position. So the alternative states, in the population from which the study sample was randomly selected, the mean score on the XYZ assertiveness scale is not equal to 100 points. The alternative hypothesis, as just mentioned, always negates the null. So if one hypothesis is true, the other necessarily is false. If the null is true, the alternative, by definition, is false. Hypotheses pertain to the population. The researcher has data only on the sample. The researcher never knows with certainty which hypothesis is true. Hypothesis pairs always pertain to populations, and so for simplicity, I'm not going to state that this is the case in most of the hypothesis pairs that I present from this point forward. I don't bother to state this because it's always the case. Now, in the interest of pragmatism, I'm going to make some generalizations. It is indeed the case that most of the time the null hypothesis states that two variables are unassociated. So the specific form of the null varies according to the types of variables that are involved. So it is the case that where both variables are categorical, the null typically states that percentages, that is to say proportions, are equal. When one variable is categorical and the other is numeric, almost all null hypotheses state that means are equal. And finally, when both variables are numeric, most null hypotheses state that Pearson's R equals 0. So we will look at hypothesis statements for different kinds of variables in a sec, but do note the common theme across these three statements. In each case, the null is stating the absence of association. So as a for instance, when percentages are equal, variables are unassociated. And so the core idea is that the null is often stating that in the population from which the sample is randomly selected, two variables are unassociated. So here is a typical hypothesis pair for two categorical variables. Null. The percentage of teens who become pregnant in prevention program A is equal to the percentage of teens who become pregnant in program B. Alternative. The percentage of clients who become pregnant in prevention program A is not equal to the percentage of teens who become pregnant in program B. Now, here's an example of a hypothesis pair where we have one categorical variable and one numeric one. The null mean self-esteem scores of women and men are equal. The alternative mean self-esteem scores of women and men are not equal. And finally, here is an hypothesis pair involving two numeric variables. In this situation, the null states that the number of visits of family members and the level of depression of nursing home patients is equal to 0, and the alternative states that this is not the case. Again, do note that each of our nulls here is stating the absence of association. Again, here the null is stating absence of association. Indeed, most null hypotheses state that variables are unassociated. It is the case that most alternative hypotheses state that variables are associated. I mean, hopefully this makes some intuitive sense. The alternative is negating the null here. You've just had a look at some hypothesis pairs, so that let's summarize what the alternative states for different types of variables. For two categorical variables, the alternative is typically stating that percentages are not equal. So for instance, with our pregnancy prevention example, it stated that the percentages who become pregnant in programs A and B are not equal. In the situation where one variable is categorical and the other is numeric, the alternative is typically going to state that means are not equal. So in our self-esteem example, the alternative was stating mean self-esteem is not equal for women and for men. And finally, with the Pearson's R, the alternative is going to state almost always that Pearson's R does not equal to 0. So when Pearson's R doesn't equal 0, I mean, that's in essence asserting that there is some linear relationship. So the core idea then is that the alternative, pragmatically, that is to say, almost often in introductory stats, it carries the notion that in the population the variables are indeed associated. There are two fundamental types of hypothesis pairs: directional pairs and non-directional pairs. A non-directional hypothesis statement does not state a direction. In a non-directional hypothesis pair, the null states equal. The alternative states not equal. All of the pairs that we've presented so far have been non-directional hypothesis pairs. A directional hypothesis statement does state a direction. In a directional hypothesis pair, the null is going to state either the condition less than or equal to, or it's going to state the condition greater than or equal to. And the alternative is going to negate the null. It's going to state the logically opposite condition. So if the null states less than or equal to, the alternative is going to state greater than. If the null states greater than or equal to negate the null, it must be the case that the alternative will state less than. So, I mean, whatever direction the null states, the alternative is going to state the opposite. If the null states less than or equal to, the alternative states greater than. If the null states greater than or equal to, the alternative states less than. Here is our teen pregnancy example expressed as a directional pair. That is, we're going to be using greater than and less than in our pair. So, null. The percentage of teens who become pregnant in program A is greater than or equal to the percentage who become pregnant in program B. Alternative, negating the null, the logically opposite condition. The percentage of teens who become pregnant in A is less than the percentage who become pregnant in B. Let's look at a correlation example. The correlation between family visiting and level of depression of nursing home clients is greater than or equal to 0. Alternative, the correlation between family visiting and level of depression of nursing home clients is less than 0. So the alternative carries the logically opposite condition. Soon we'll get into which direction, when we use a directional pair, which direction does the null state and which direction does the alternative state. But for now, let's just go ahead and express the directional pair for this current example, but reversing the direction. So if we reverse the direction in the null, we would state the correlation between visiting and depression is less than or equal to 100. And then therefore the alternative has also got to shift its direction. So we're going to shift from less than to greater than. So the correlation between visiting and depression is greater than 100. So this hypothesis pair reversed the direction of this one. Both of these are examples of directional pair. So one question is, when do you use a directional pair and when do you use a non-directional pair? And I'll just mention there are some situations where only a non-directional pair can be used, but these are treated almost as exceptions, and we get to those, I think, in Chapter 19. So most of the time you're going to have the option to be able to choose a directional or a non-directional pair. So when do you use one type of pair and when do you use the other? So ultimately this is your choice. So what I can offer are recommendations. It is typically the case that directional hypotheses are used when prior research, theory, logic, or even common sense provide really strong expectation that the study result will be in a particular direction. As an example, presume that we very strongly expect to find positive correlation between the amount of violent TV watched and the amount of violent behavior that kids exhibit. Perhaps there is a great deal of prior research that says that this is so, and indeed there's strong theoretical expectation that this is so. So let's suppose that our situation is that we strongly expect to find this particular result of positive correlation. Given that we have strong expectation, almost compelling expectation, the directional pair is a good choice in this situation. This is the kind of situation where you use directional pairs, where there's strong reason to think that the result will be in a particular direction. So we've established that it's your choice between the directional and the non-directional, and we've mentioned that directionals are used almost exclusively, which is to say they're not used when this is not so. They are used when there's really strong expectation of a particular result in a particular direction. So we're going to go ahead and develop a directional hypothesis pair. So the next question is, given that we've reached a decision to use a directional pair, which hypothesis, the null or the alternative, is going to state the direction that is consistent with our expected result. And the answer is that when you formulate a directional pair, the alternative hypothesis states the direction of expectations. So our expectation is for positive correlation between violent TV watching and actual violent behavior. So this null is stating the opposite direction. So the null here is stating that the correlation between the amount of violent TV watched and the amount of violent behavior is less than or equal to 0. The alternative here is stating the direction of expectation. So we're expecting positive correlation. Positive correlation conveys positive relationship. So the alternative states that the correlation between the amount of violent TV watched and the amount of violent behavior exhibited is greater than 0. So here, as must be the case if you use a directional pair, the alternative is carrying the direction in which we expect the results to be. Now, back to the question of should you use a directional pair or a non-directional pair? Again, the non-directional pair is basically using the logical operators equal in the null and not equal in the alternative, whereas the directional pair is injecting the notion of direction. It's using the operators less than and greater than, or more particularly, less than or equal to versus greater than, or greater than or equal to versus less than. I mean, what I'm trying to say is the equal to condition is always stated in the null. So the null states the direction opposite to expectation and also the equal to condition, and the alternative states the greater than condition. But which pair should you use? Now, different researchers will disagree here, but it is indeed the case. I mean, this is not up for debate. I mean, non-directional pairs are much more common. I'm hard-pressed to give you a percentage, but I think perhaps 90 to 95% of the pairs that you see are non-directional. So the directional pairs are traditionally reserved, for those situations where there's strong expectation of direction. So much of social science research is comparatively new that it is somewhat unusual for us to have strong expectation of direction. Oftentimes we're in reasonably new areas and we don't have that strong expectation. So, I mean, my recommendation to you, and others might recommend differently, is that you reserve the use of directional pairs for situations when you have very strong, in essence compelling, expectation that the result will be in a given direction. Okay, that's going to conclude this video, and the next video is going to explore in greater depth how hypothesis pairs are used in significance testing.